in for a little bit. So I am very excited to introduce our speaker. Tamara Broderick is an associate professor at MIT, and we'll be talking about finite sample robustness metrics.
Thank you so much, and thanks for having me. Thanks for everyone who's here, and thanks to the people who turned their cameras on. I appreciate it. It's nice to be talking to people. So yeah, today I'm going to be talking about a check that you can run on your data analysis, namely a check to see if there exists a tiny fraction of your data that if you dropped it would change your substantive conclusions. So before I proceed, I just want to note that this is work with my fantastic postdoc, Ryan Giordano, and our amazing collaborator, Rachel Meager, who's a professor at the London School of Economics. If you have any chance to collaborate with them, they are a joy. Okay, so in some very, very broad sense, today we're talking about, when can I trust my data analysis? In some sense, the promise of having, more and more data these days and better computation means that we can run data analyses that drive life-changing decisions. These could be in medical advances, in individual medical care, they could be in cybersecurity, they could be in personal finance and financial policy writ large. And I'd say, in general, if I have some really important program, I don't want to just accept its output. I want to run a whole bunch of unit tests to really check that that program works. And so in some sense, we could ask, what are unit tests for a data analysis that are specific to a data analysis? Now, obviously, that's going to depend on the analysis. And probably you should have a ton of them, not just one. And so I'm really just suggesting, I'm not being exhaustive about this question, I'm just suggesting one possible unit test that might be pretty general purpose today. And namely, the idea is, if I were to drop a very small fraction of my data, would my substantive conclusions change? Does there exist a very small fraction of my data that I might drop and change those conclusions? And I think in many cases, we would be worried if this were the case. So why doesn't everybody check this already? Well, it's basically astronomically expensive to check, as I'll go into in a bit more detail shortly. And so what we're going to provide is a fast and automated and an accurate approximation. And so just to give you sort of a teaser of what this can do, we looked at a very influential study of microcredit. So microcredit is these small loans to individuals in impoverished areas. And the hope is that it helps bring them out of poverty. And you want to check that with a data analysis. And we find in this very influential study that just one data point drives the sign of the effect. If you remove this one data point, you go from the difference between microcredit helping and hurting people. Okay, so we'll learn all about that study and all about this approximation as we go forward. So what in particular are we going to do? We're going to start by talking about this idea of dropping data subsets. I'm going to spend a little bit more time on talking about why is this a check that we would want to do on at least some data analyses. I'm going to talk about what exactly does this look like? What does it really mean to drop data subsets and to check how sensitive you are to that? And then we're going to see why is this so computationally expensive? Why can't we all just run this right now? And why do we need an approximation? And so at that point, we'll talk about what is the approximation? Why is it fast? And why is it automatic and easy to use? And then we'll spend a little time just saying, well, what does this look like in practice? We're going to see that it flags some analyses as non-robust and other ones it does not flag. And we're going to note that it's not information that you would just get from the usual things that you run. So you can't just expect to get rid of gross outliers and assume that you won't be sensitive in this way. You can't rely on small p-values, making sure that you're not sensitive in this way. Just because you have light tails doesn't mean that you're not sensitive in this way. So this is very different from, you might be familiar with like Huber robustness. It's a different type of robustness. And we're roughly going to see that somehow this type of robustness that we're looking at today is going to be something like a product of low signal to noise, where for the moment, signal is roughly the amount of information about what we care about, and noise is the error that's sort of making it hard for us to access that information. Okay, so let's start by saying, when do we care about dropping data subsets? And I think a really important thing to recognize here is that, a lot of times, and I'm going to do this in this talk too, we use words like sensitive or robust to describe an analysis. And those words are meaningless on their own. What they really mean is sensitive to something, robust to something. You can't just be sensitive to nothing. If you had an analysis that didn't change whenever you changed your data, that would be a pretty useless analysis. Like it's got to change for something. And so we really have to ask, what types of sensitivity are bad types of sensitivity, or at least concerning, things that we would want to follow up on. And of course, this is going to vary by problem. If you have some cybersecurity problem and you think that somebody might crack into your data safe and change your data in some arbitrary and malicious way, that's something that you want to guard against. But I think in a lot of the social sciences and sciences, there's not some malicious person who's coming in and poisoning our data. It's more like there are just things that might have gone wrong along the way, and we want to check that we're not sensitive to them. Okay, so what are those going to look like? Well, let's look at economics for 3 reasons. One, it does have very important applications. These applications are guiding policy. They're affecting all of our lives. 2, in the course of this paper, I discovered something that I'm sure economists all know. It is wonderfully reproducible as a field. Every single major study that we reproduced, we did exactly. There was all the data, all the code was available. I mean, it was just really fantastic. So our experience was really great here. And 3, we were able to work with an economics expert. So Rachel Meager is just totally fantastic. And so that drove us to these applications. But I think a lot of the things that we're going to say today are not specific to economics. Okay, so let's look at economics. Well, what are some concerns we have in economics? Well, one, it is definitely the case that small fractions of data are often missing, not at random. Suppose you got your data via a survey, or you called some people up and some people, didn't respond, or they don't have phones. This is definitely going to be potentially some bias in the sample. And so I would worry if my major conclusions depended on a very small fraction of my data. The policy population, the population to which you may one day apply your policy, is definitely different from the population that you analyzed. For one, you might have done some analysis in a particular state and you want to apply it to other states. If you did it in a country and you want to apply it to another country, even if you did it on a population and you are just going to take that exact same population a few years later, that population has changed. The people in it changed over time. Maybe some people left a village or something like that. And so again, I'd be really concerned if my major results depended on a very small fraction of my data. In economics, like in many areas, they are typically reporting a convenient proxy like a mean. So basically, all the usual statistical tools tend to report something that kind of looks like a mean. But let's say that I'm looking at average profit in my village, and Bill Gates walks in. Suddenly, even if everybody else was suffering from worse profit after some intervention, suddenly the profit is fantastic. And that's not what we want to get at, right? Like usually we want to say something like, is microcredit helping people? And that means, is it helping a lot of people? And so if Bill Gates is the determining factor, that's not like a really good intervention. And we'd want to know if we removed Bill Gates, if it would still be a good intervention. And models are necessarily misspecified. I think this is true not just in the social sciences, but across the vast majority of the sciences. I mean, maybe some people in physics really know that something is Poisson, but the rest of us have to deal with real life where things aren't quite what we're imagining. And so we'd be worried if they really depended on a small fraction of our data again. Okay, so in all of these cases, we'd be concerned if dropping a small fraction of data changed our conclusions. And again, they're not specific to economics. I think these are things that we encounter in really most of the sciences and social sciences. Now, it's worth noting there are definitely analyses where you think a small fraction of your data should be driving your conclusion. So here's an example due to Rachel. What if I'm studying a large population and I'm studying murderers within that population? I hope that within that population, murderers are a very, very small proportion of the population. And so it should be that that's a small fraction of my data. Nonetheless, my audience should know that maybe the 6 murderers is the relevant number of data points that I have and not the 30,000 people that they came from in terms of size of my data. Okay, so these are reasons we should care about dropping some small fraction of our data. So let's look at what that looks like exactly. Okay, so we're going to call that fraction that we're dropping alpha. It's technically between 0 and 1, but we're imagining it's very, very near 0, like 1% or less. Now, what we want to do is we want to say, what would we worry about in our analysis if we drop the small fraction of data? Where I'd argue we'd worry if our decision changed. At the end of the day, we're making some kind of decision, and it might be based on the sign of some effect we're measuring, in which case we'd be worried if that sign changed. It might be based on some significance of some effect that we're measuring, in which case we'd worry if that significance changed. Maybe we make a decision if both sign and significance align, if we have a positive effect that's statistically significant. then we'd be worried if that changed, and so on. Okay, so in all of these cases, we're measuring some quantity, like maybe an effect. And then we're asking, how much does it change when we drop the data? Isn't it enough to change a decision, like maybe change the sign? And so keeping that in mind, let's define a few quantities that we might be interested in. First, let's define what we're going to call the maximum influence perturbation. The idea here is what's the largest possible change? So again, we're measuring something of interest, like an effect. What's the largest possible change in, for instance, that effect that we get by dropping an alpha fraction of the data? And then we can ask, once we know the largest possible change, did it change the sign? Did it change the significance? And so on. Now, of course, once we know that, especially if it's very small, we want to identify what were the data that made this change. So let's call that the most influential set. These will be the data that we drop to achieve this change. Now, something else we might want to be interested in is what we're going to call a perturbation inducing proportion. So the idea here is, what is the minimum data proportion we can drop to achieve a certain change? So how little data, is it very little? How much would it take to change the sign of an effect? And here it might be the case that there's no data we can drop to change the sign of an effect. Maybe it's all well separated and we're doing some classification, and let's call it NA then. Okay, so this all sounds good. Again, I think pretty straightforward concept, something that seems like we'd all love to check in our data analyses. So why don't we all do it? Well, let's talk about what would be involved in doing it. Suppose I want to find the maximum influence perturbation. Well, one way I could do that, certainly the seemingly straightforward way, is to just take every data subset with size at most alpha fraction of the data, drop it, rerun my analysis, and then do that again and again. Okay, so what's the cost of doing this? Well, let's take a really simple example of just 400 data points. That's a pretty small data set. And suppose I'm interested in data sets of size 1% or less. So alpha is 0.01. Well, that means I'm going to have to drop all the data sets of size 4, of 3, of 2, et cetera. Let's just look at 4 for the moment. Let's just say I drop all the data sets of size 4. 400 choose 4 is over 1 billion. And so if my original data analysis took 1 second to run, this check takes over 33 years to run. Now, yes, we have massive parallelism now, but this isn't a problem that massive parallelism isn't going to solve. In fact, as you get more data points, which every example that I'm going to show coming up has more data points, this gets combinatorially worse. And if your data analysis takes more than 1 second, this gets linearly worse. Okay, so this is the problem. This is why we need some kind of approximation, why we can't just do this directly. And so before I tell you what that approximation is, let's take a look at it in practice. So hopefully you're motivated to care what the approximation is. Okay, so we're going to look at exactly that microcredit example that I talked about before. So Angelucci et al. 2015 is this fantastic paper. So it turns out there are 7 different papers. Each one did a randomized controlled trial, and these are just extremely influential in the field, and they all examine the effect of microcredit in a different country. And so this happens to be the largest of these papers in terms of number of households involved. There were 16,561 households. And again, fantastic reproducibility and data sharing. These are really great papers. Now, it turns out that in this model, you could include a ton of different covariates, and other people, like Rachel's previous work, has shown that just all those extra covariates don't matter. What really matters is just the microcredit indicator. So let me describe what's going on here in this model. So there's this one covariate for the nth data point, and it is an indicator of whether or not this household received microcredit. It's 1 if they received it, and it's 0 if they did not. Now, at the end of the day, we sort of want to measure, did this help people? Now, it turns out all these households have small businesses. And so one way that we might quantify how much it's helping people is how much profit did that business get? And so the parameters of this model are theta naught, which is like the sort of average profit if microcredit didn't exist, and theta 1's like the effect of microcredit. How much does microcredit help? It could be negative, it could be positive. Okay, so if you look at the original paper, they run an ordinary least squares regression. They get out that theta 1 is negative 4.55 US dollars purchasing power parity every 2 weeks with a standard error of 5.88. So 1, this is saying that microcredit is hurting because it's negative, but 2, it's not a statistically significant result. The negative 4.55 is not 2 standard errors away from 0. Okay, so let's see what happens if we drop a little data. So the first thing to note is that our approximation takes 2 seconds to run. If you looked at running this for, actually rerunning every data analysis, it would take over 10 to the 42 years. So you wouldn't want to do that, again, even with parallelism. We quickly find that there is one household that you can remove that changes the sign. So it changes it from negative to positive. Now you might be thinking, but it's not statistically significant anyway, so who cares about that? Well, there are 15 households that you can remove that change both the sign and the significance. So now this is a positive result that is significant. And remember, 15 here is less than 0.1% of the data, so it's not even 1%. Okay, now we actually have quite a lot of theory that suggests that our approximation is very close to the ground truth, to actually running this exactly when you're looking at a very small fraction of your data. But you don't have to trust any of our theory, because as soon as we identify the data points that are the problem, we can just tell you that, and then you can rerun the analysis. And you don't have to rerun it 10 to the 42 times or whatever. You can just rerun it once extra. So now you've just run 2 analyses. That's probably not prohibitive. And that's not too bad. And in fact, we do that in this case, and everything checks out. Okay, so now you might be thinking, the problem is non-significance. We're going to see an example later in the talk that turns a statistically significant result into not a statistically significant result. You might be thinking the problem is gross outliers. We're going to see later in the talk that getting rid of outliers does not necessarily change the non-robustness. You might be familiar with things like Huber robustness. And so you might be thinking, the problem is that they're reporting something like a mean, or maybe there's secret heavy tails in the data. And we're going to see later in the talk that that is a different type of robustness. And this is complementary and it's picking up something else. You might be thinking, hey, if I used Bayesian inference, I wouldn't have this problem. I'm not going to cover this in the talk, but we cover it in the paper. You do, or you may still have this problem. Bayesian inference is not a panacea here. Okay, so hopefully at this point you're motivated to hear what is this approximation and how is it going to work? And so that's what we're going to talk about next. Oh, and we will see that one issue that is getting more at what's actually happening here is this idea of signal to noise. Okay, so far we said, when do we care about dropping data sets? You know, these small fractions of the data. How do we drop it? Why is it computationally expensive? And because it's so combinatorially computationally expensive, we need an approximation. And so that's what we're doing next. We're going to describe the approximation. Now, before I go on, I want to emphasize, you could actually just go and use our package right now. It's in R. There used to be some Python dependency if you checked it out before. There is no longer that Python dependency. So no worries, it's just all in R. You could just run this on your analysis and be happy, and you don't need to know everything that's going on behind the hood, but now we're going to talk about that. So you can have a better understanding of what's going on. And then we'll also talk about some analyses and how this looks in practice. Okay, so in order to set up the approximation or to describe the approximation, first I'm going to describe a sort of generic data analysis. So in our generic data analysis, we'll have some data. Oops. Somebody seems to be drawing on this. I think annotations may not be turned off. Let me see if I can, if I have control over that or if that's a host thing. Okay, I was able to turn it off. Great. Okay, so cool. So we have some data to start. Let's call it D sub n. So n indexes the nth data point. An example of this might be if I were doing some kind of supervised learning, or like regression, and so I might have a collection of covariates xn and some responses yn, but your data doesn't have to look like this. It could be just about anything. Now next, I'm going to have some parameters. Let's call them theta, and in this case, we are going to assume that they're Euclidean. And now I might typically have some loss that relates my parameters to my data point. Let's call it f. And a way that I might talk about loss over the entire data set is to sum over capital N data points, the loss over the individual data points. And then a way that I might often estimate my theta is by minimizing the loss. So I get my estimator theta hat when I do that. Okay, so obviously any loss minimization problem fits into this framework. Maximum likelihood would also fit into this framework. You can have FB or negative log likelihoods. It'll turn out that we actually do things that are more general than this framework, but I think this is already pretty general and easy to talk about. Okay, now typically our analysis doesn't end there. We actually identify some quantity of interest that we're interested in talking about and that we're going to use to make our decision. So for instance, this quantity of interest might be an element of theta. Like let's say it's the pth dimension of theta. So this was an example of this, or this is what happened in that microcredit example. We learned theta naught and theta 1, but we really just kind of made decisions based on theta 1 at the end of the day. Now, you might be interested not just in theta hat on its own, but you might be interested in saying something about significance, in which case you would actually look at your quantity of interest as being theta p plus or minus 2 standard errors, potentially. Or you might have some other quantity of interest. But this is sort of the thing that you're going to use to make your decision. Okay, so now let's talk about a framework where we can use the same notation to talk about our original analysis and dropping data subsets. So in particular, we're going to imagine that we give every data point a weight. So data point 1 gets weight W1, data point 2 gets weight W2, and we collect all of these weights in a vector, let's call it W. And in my original analysis, every data point gets a weight of size 1. And we can call that the all ones vector, or 1 sub n. Now, when I drop a data point, it's like I'm taking the weight for that data point from 1 to 0. If I drop a few data points, it's like I'm taking the weights for all those data points from 1 to 0. And so it follows that there's a one-to-one correspondence between every drop data subset and a certain set of W's. And so how does this change our analysis up at the top? Well, we're going to change the loss. So in particular, we're going to take our losses and we're going to pre-multiply them by the weights. And so if I want to solve my original problem, I'll just put all the weights in as 1, and I get back my original problem. If I want to solve my problem with some data points dropped, some of these will be 0, and that will just get rid of those loss terms. Okay, so implicitly here, our theta hats now are functions of W, as they should be. Essentially, this is like saying they're functions of the data. It's just a way of expressing that. And so our quantity of interest, in turn, is a function of W. And so that could be via theta, because theta hat is now a function of W, but it could also be another way. So for instance, when you estimate a standard error, it might have some W dependency beyond just theta hat. Okay, so at this point, we've just sort of had this sort of unusual way of describing dropping a bunch of data subsets. We haven't really done anything yet, but this will really set us up for the approximation, which we're going to show on the next slide. Okay, so first of all, on this slide, I just have the general data analysis as a function of W at the top, and then this idea of the quantity of interest right below it. So these are just repeating from the previous slide. And here's the approximation. Let's just do a Taylor expansion in W. When we're dropping a very small amount of data, we're changing that all ones W vector very little. And so maybe a first order Taylor expansion will be a pretty good approximation. Spoiler alert, it is. Okay, so let me walk through everything that's going on in this equation. So first of all, what we would like to do, and we can't do, is we would like to, for every one of these W's, this combinatorially large set of W's, we'd like to compute phi of W. And we can't, because that's expensive in the ways that we just described. And so instead, we're going to use a linear approximation, let's call it phi lin. And that is literally just a first order Taylor expansion. So this next part is just writing down a first order Taylor expansion in W. So first we have the 0th order term, phi of the all ones vector. This is literally what you get by running your original data analysis. Because you just run your data analysis to get theta hat of all ones, and then you find out what your phi of all ones is. And so like this is a sunk cost, like you got to run some data analysis. The second term, the linear term, is basically the difference in the W's together with 1, or between W's and 1, and the derivative. So the derivative here is the derivative of phi with respect to W, because that's what we're doing this Taylor expansion in. Now, if you're familiar with influence functions, this might look somewhat familiar. We're going to call this the influence score of the nth data point. It's the only thing in this, equation that it might be non-trivial to compute, but it turns out that it is trivial to compute in the following sense. So we can write a formula for the influence score by using the implicit function theorem. So the implicit function theorem is to get us the derivative between theta hat and f, or the sort of, the theta hat and W, which will go through F. And then the chain rule is to get us phi relative to theta hat. Now, at this point, we have something that depends on derivatives of F and derivatives to do with phi and theta, which, first of all, I want to note, we are assuming differentiability. So that is somewhat limiting, although I think many analyses will still fit this, but we are assuming that differentiability. But you could still be wondering, and I think traditionally something people wondered is, oh gosh, am I going to have to write down derivatives? Nobody's going to use your method if they have to sit and write derivatives for a while. And luckily, no, because thankfully we have modern automatic differentiation tools. And so you just have to write what is your problem, and then the computer does it for you. If you happen to not be familiar with automatic differentiation, I want to point you to this excellent survey by Baden et al. 2018, which also contrasts with numerical and symbolic differentiation. But basically, automatic differentiation has been pretty revolutionary, despite being a pretty straightforward concept for deep learning. And even on the probabilistic side, languages like Stan that have really revolutionized Bayesian inference. And it just makes it so that we don't have to compute these derivatives by sort of having a representation, or your computer has some kind of very basic representation of any kind of calculation that it does, and you can use the chain rule on that representation. And so that's all that's happening with automatic differentiation. But the point is, you don't have to write down derivatives. Everything gets done for you. Okay, so let me make a couple of points about this. So one, we were concerned originally that we'd have to run this combinatorially large number of data analyses, and now we just have to run one to get that phi of the all ones vector. Now we still have the concern that it looks at the moment like we still have to calculate phi lin for every one of these combinatorially large number of W's, and so that's not solved yet. We'll have to solve that on the next page. But at least we don't have to do that many data analyses. Now, I did mention, I've sort of set this up as being something like an M estimator. The reality is our method runs for Z estimators. And so you could think of solving this original optimization problem by taking a derivative and setting it to 0. But there's actually quite a bit more that you can do with Z estimators. So for instance, you can do multi-stage optimization. So an example of that in economics is instrumental variables regression. In biology, we've seen cases where people, you do some kind of B-spline and then you do clustering. Anything that you have that has the form of a Z estimator is still just fine. And so if this data analysis looks familiar and it's good for you, that's fine. But if you want to do more general things, I guess I want to suggest that we might still be able to do those more general things. And finally, before I leave this slide, I just want to note a really natural question is, why stop at a first order Taylor expansion? Why not keep going? And one, the answer for the purposes of today is that the first order seems to work fine, and so we don't need to keep going. So that's great. A broader answer is that there are some cases where it seems like we might want to keep going, like maybe approximating things like the bootstrap. And so we have some very early work that I've cited at the bottom that's just on the archive, and we're still working on it, and it's pretty messy right now. But if you're interested, there is some stuff that's up there. Okay, so let's deal with this issue of it still looks like we need to get phi lin for all the W's, which we couldn't do because there are just combinatorially too many W's. Okay, so here we just have everything from the previous slide except for the bottom part. Now, essentially what we're trying to do is find the worst case change in this quantity of interest. Like, how bad could things be? And that's really what we're going to take advantage of here, so we don't have to compute this for every W. So what we'd like to do is we'd like to say the worst case change in the exact case. And in that case, it seemed like we had to compute phi for every single W to find this change, and that's too much. But in this approximate case, this change has a really convenient form. So I'm literally just going to use the line 2 lines above, the Taylor expansion line, to rewrite this as this sum. And this sum, you'll notice, has this Wn minus 1 part. Well, most of the time, Wn is 1, because we're only dropping a few data points. And so really, we can rewrite this sum as a sum over the cases where Wn is 0. Those are the data points we've dropped in this particular W. It's a sum over these influence scores. Okay, so why is this useful? Well, here's an algorithm that we can use. Compute all the influence scores. This is a linear time operation. You just compute one of them per data point. It doesn't change with the different W's, so you just have to do it once. Sort all of the influence scores. Technically speaking, this is n log n. It's not linear, but I have never had a problem where sort was the bottleneck, and I suspect that your problem does not have sort as the bottleneck. And finally, remove the largest influence scores. So now you know how to make the biggest change, remove just one data point, and then you know how to make the second biggest change, remove the second data point, and so on. And so how does this get us what we want? Let's talk through those quantities that we said we were interested in before. We wanted to get the maximum influence perturbation, the largest possible change by dropping alpha fraction of the data. So now we're going to get the approximate maximum influence perturbation by first dropping the biggest influence score, then dropping the second biggest influence score, and doing that until we've dropped at most alpha fraction of the data. And that's the biggest approximate change we can get. Along the way, we could remember the data indices that we dropped, and that's the approximate most influential set. It's the set of data points that we drop to get the approximate maximum influence perturbation. Now, again, another idea might be we want to find the minimum data proportion to achieve a certain change. And so here what we can do is we can drop the biggest influence score and then the second biggest influence score, and we just keep dropping until we achieve a certain change, like a sign change or a significance change or whatever it is we're interested in. And we return NA if none. Now, it's worth noting in this case that the NA really just means in the approximate case that we could find no difference. The nature of this Taylor series approximation is such that it is accurate when we're dropping very few data points, and it's less accurate when we're dropping a lot of data points, because then W is pretty far from 1, but that's exactly what we want it to be. Because if we're dropping very few data points and we get a big change, then we think our analysis is really sensitive and we want to know what those data points are and we want to know what's going on. If it takes a ton of data points to change our analysis, well, that's pretty good. I mean, our analysis should change eventually anyway. And so it doesn't matter if we get the numbers exactly right then, because we just wanted to know, were we not robust, and everything's already fine. Okay, so this is the approximation. We have now covered the approximation. This is like the idea. This is what we use in everything that we're describing. And so now let's check it out. Let's see it in some more examples. So first I'm going to do a simulated example, and I'm going to do 2 more very influential economics papers. Okay, and essentially, in some sense, what we're going to be asking in a lot of these examples is, hey, for this type of robustness that we're discussing, what makes an analysis non-robust? Okay, so a nice thing about a simulated example is that you control everything. You know, everything is perfectly specified and all of that. So let's do a simulation from a linear model with Gaussian noise. Doesn't get much simpler than that, especially if it's one-dimensional. So here, theta is one-dimensional, xn is one-dimensional. Everything's pretty nice. So we're going to simulate epsilon n. I mean, this is just part of our likelihood here. We'll say that epsilon n is normal with its own standard deviation, sigma epsilon. We can simulate xn, so we have to make the xn because we're simulating them. We can do that from another normal with its own standard deviation, sigma x. And then finally, we have to choose the theta again because we're simulating things. Let's just choose the theta to be -1. Okay. So let's now generate, we can simulate a data set of size 10,000, and we can ask, what does it take to flip the sign of theta hat? In particular, we're going to vary aspects of the model and see how that changes. And so in particular, the 2 things we're going to focus on here are what may be called the signal and the noise. So you can think of the signal as sort of the strength of the effect, or what is the change that we want to make. So here we're trying to change the sign. So we have to make a change, or delta, of size theta hat to go from theta hat to 0. I probably should have like an absolute value here, but you know, that's the idea. Okay, now what is the noise? This is a little subtle, and then I'm going to get back to like the nice intuition. So we show in our paper, you know, so first of all, the noise is sort of like what makes this a hard problem, you know, how roughly big of a change can you get? So we actually show in the paper that the approximate maximum influence perturbation, the thing that I described on the last slide, like the metric that we really care about, breaks down as roughly a shape term times a scale term. The shape term pretty much doesn't vary from problem to problem. I mean, it's roughly constant, and the scale term is what's really driving things. And in particular, it turns out the scale term is an estimate of the scaled asymptotic standard deviation. Now, in this particular problem, we can get a lot more intuition by saying, what is that actual value? So it turns out the actual value is pretty close to sigma epsilon over sigma x. So why does this make sense? Well, as sigma epsilon gets bigger, the epsilon n term dominates in the original linear regression. And so there's not a lot of information about what theta is. And we expect this to be a pretty unstable problem. Whereas if sigma x gets really big relative to sigma epsilon, then the theta xn term is dominating. And there's a lot of information about what theta is, and we expect this to be a pretty stable problem. Similarly, if the signal increased, if theta increased, we would expect this to be a pretty stable problem. And so roughly what's happening here is that this becomes a more stable problem as signal to noise increases, and this becomes a less stable problem as signal to noise decreases. Let's see this in action. So what we're going to do here is we're going to do a whole bunch of simulations. Every little block in this plot is a simulation. So on the horizontal axis, we're varying sigma x. On the vertical axis, we're varying sigma epsilon. In that lower right-hand corner, where everything is gray, that's where for each one of our simulations, there was no proportion of the data we could remove to change the sign. On the diagonal, there is a proportion of the data we could remove, but it's pretty big. And as you get to higher sigma epsilon and lower sigma x, there's a smaller and smaller proportion of the data that you have to remove to change the sign, as expected. And we see this pattern for changing the sign in significance, changing the significance. These are sort of the quantities of interest in this problem. Okay, so I want to highlight two things. One, the low signal to noise ratio seems to be driving non-robustness here. It gives you a sense of sort of what's going on with non-robustness. And two, this is different from other things. Misspecification is not the issue here. Everything was perfectly specified. We use the same model that we generated everything from. If you're familiar with Huber robustness, basically a very common type of robustness that you see a lot in statistics, you might be thinking means are the problem or heavy tails are the problem. Well, here we see using means that are both robust and not robust, and we have other examples of that later. And we don't have any heavy tails. Everything is light-tailed, everything is Gaussian. So that's not what's driving this. Okay, so this is a simulated example. Let's check out a couple of real data examples. Okay, so there's this Oregon Medicaid study. It's super duper famous. You probably read about it in the news at some point. And we're going to see here that a small p-value is not decisive.
Can I ask a question?
Please do. Yeah.
Hello, I'll put on my camera. So can you draw like a scatter plot of those 10,000 points and tell me which 30 points you have to eliminate to change the sign? So I have some intuition about how it's even feasible.
Yeah. So something I'm gonna okay. So like spoiler for 2 slides from now. So in linear regression, something that we can actually show is that the influence score. So the influence score is again that thing in the approximation that we're taking away from the top to get the change. The influence score is actually the residual times the leverage. And so this gives us at least a little intuition about why these aren't just pure outliers in terms of a residual sense, because they have to have both a big residual and a big leverage simultaneously in order to have a big influence score. And so then those would be the ones they would remove. And I think, yeah, I should, unfortunately, I don't have a scatter plot to share, but I totally should. And then I think we could see, how this interaction happens, at least in the case of linear regression. And I suspect that this gives us at least a little intuition about other cases. One thing that I will say is that you get the data points when you're doing this. And so you can always make that plot very easily because it's telling you which ones are the problem. Cool. Okay, let's look at this Oregon Medicaid study. So this is Finkelstein et al. 2012. Again, love these papers. They're fantastic. So very famously, there was this lottery in Oregon where the winners were able to sign up for Medicaid. And so this is sort of a natural randomized controlled trial where we can decide, oh, what's the effect of Medicaid? And this might lend insight into the effect of Medicaid. There are actually quite a few analyses in this paper, but one of the analyses is the sort of directly looking at the effect of the lottery on health outcomes. And even then, they look at quite a few different health outcomes. I'm just going to put one right here, although we look at all of them in our paper as well. So one potential health outcome is to say 1 year after people started receiving Medicaid, what was the number of days that they had of no impaired activity over the last 30 days? So in this case, there were over 21,000 data points. These are survey responders. So again, we're thinking about all those ideas that we talked about earlier in the talk that, there might be issues of non-response bias, the population changing, all of these things are very relevant here. And there's a significant effect. In fact, if you look at this paper, their p-values look fantastic. They're very often less than 0.01. Everything, you know, comes off as very significant. But this analysis, this sensitivity analysis, is able to flag 11 data points. That's just 0.05% of the data, much less than 1%, much less than 0.1%, that changes significance. Okay, let's look at another example. This is a cash transfer study. So in this case, we're going to see that you don't always get flagged as non-robust. I think there's sort of a bias in a paper like this that we want to say, hey, look, we can flag things, we can point things out, but of course not everything gets flagged as non-robust. In fact, we've had some people tell us about their own analyses already that also did not get flagged as non-robust. We're also going to see that removing outliers isn't a panacea for basically the reasons that we just discussed in the question. Okay, so this is Angelucci and DeGiorgi, 2009, and another really lovely economics paper. And there were two studies, essentially, or at least that we're going to focus on here. So one is looking at the direct effect of cash transfers for poor households on household consumption. So the idea is, let's give these poor households cash, and then the question is, does that help them? And that's always, hard to measure, but one way to measure it is household consumption. Now, a really interesting aspect of this study is that the randomization was on the village level. And so you can ask, hey, there were all these households that didn't qualify for the cash transfers because they weren't poor enough. Did they benefit anyway? Is there some spillover effect on the non-poor households in the same village? Pretty cool idea. So let's look at each of these in turn. So first, let's look at the poor households. So in this case, there were over 10,000 data points. It turns out that you can check that our approximation tells us that if you want to try to change the sign, the significance, sign and significance, it's always requires like over 4% of the data. It seems like a lot of the data. Again, eventually, like these things should change. And so this doesn't seem too concerning. The reason there's a range is because of the sign, the significance, et cetera. Although again, it's worth also noting that as soon as you get to these big collections of data, it's not certain that our approximation is very good, but that doesn't matter. We just need to know that it's a lot of data. And then exactly what percentage it is at this point, I think is beside the point. Okay, so here's something that didn't get flagged as non-robust. Now let's look at the spillover study. So in this case, there were over 4,000 data points. Now this is a case where the original analysis deleted outliers. So they took all of the households with consumption greater than 10,000 units, sort of the largest response, and they deleted them. Now that didn't get rid of all sensitivity. We could still find 3 points. So when I say this, I'm saying, let's look at the analysis without those deleted points. Let's act as though they didn't exist. And it's still sensitive. So we can find 3 points, even once the outliers are removed, to change the significance of the result. Again, this gets at this idea that it's not just about being an outlier. And in linear regression, we can express this in sort of an equation, that this influence score, the thing that we're dropping to get our change, is exactly the residual times the leverage here. And so you can have a very large residual, but maybe not have a large leverage or vice versa. And here you sort of have to have both to be influential. Okay, so now we've seen this in practice. We've seen this approximation in practice. We've seen our metric in practice on 3 different real life data analyses. We have quite a bit more in the paper, more on these particular analyses, and one simulated analysis. And so let me just make a couple of additional remarks and sort of connections before we finish up. So I want to emphasize that these concerns are not specific to econometrics. I think something that if you were reading this in sort of like a very quick kind of way, you might think that our paper is some sort of gotcha for economics, and I think that's just like the opposite of the truth. I think one, it's a testament to the reproducibility in economics. I think it's just amazing that the field is so careful about these things, and I think we could all learn from that, myself included. It's not reasonable to expect that anyone in economics would have run these checks before, because it seems like you could not have easily run these checks before, and it certainly wasn't on people's minds. And finally, I expect the lessons here apply to other areas as well, not just economics. And so I just want to point that out. I think this is an illustrative set of examples, and it's really made possible by how awesome the economics field is. Okay, another point is our approximation is local. We're making this Taylor series expansion. And so if you expect that you have this highly involved multimodal likelihood landscape, then you probably think that something local around your optimization point, whatever point your optimization returns, is not capturing everything that's going on. And so at the very least, this should tell you that this is complementary to global checks. So if you can run a global check, it's probably a good idea to run a global check, but you should also think about the nature of your likelihood landscape before you understand like exactly what this is telling you. Now, if it flags something as non-robust and you can actually run that, it's still non-robust, but that just because it doesn't flag something doesn't mean you're in the clear. Okay, and of course, as we've seen a few times now, this is very complementary to other types of robustness. So I don't see any of those things. That's interesting. Let me see if I can get back in. Oh, somebody else is sharing their screen. I think anybody can share their screen is the issue. So I will try to share my screen again, but I'm relying on nobody else sharing. Okay, great. Okay, so this is complementary to other types of robustness. So I think the type of robustness, or a type of robustness that certainly seems very common and is super well studied. I mean, there's just a huge literature on things like Huber robustness. And we've seen that this is just a different type of robustness than that. That if you're looking at things like data poisoning or cybersecurity concerns or lots of concerns, that is totally appropriate. And in other cases, ours is appropriate, and they're just different. Likewise, if there is something that you care about, that you feel like your analysis should not be sensitive to, there's a good chance that this does not cover that thing. And so there's real reason to think that you should still have tailored checks if you possibly can for that type of robustness, whatever is concerning you. Of course, as usual, the challenge is how easy is that to do, but if you can do it, it's a good idea. And likewise to robustification procedures. So there's, again, a huge literature on coming up with procedures that are robust in a Huber sense. So if you do that, that's great, and that probably means something about Huber robustness, but it doesn't necessarily tell you anything about robustness in the sense that I've been describing today. And so you should still do the check. I'll just say that this work, in our particular case, grew out of a growing literature on approximate cross-validation and the use of influence functions for practical checks. So there's some fantastic work that's been done by a variety of people, sort of too many to name. And this is such an active area that I suspect that there are more papers than, I know that there must be more papers than what I've written here. But I want to just briefly talk about some of the other work that we've done in this area. So we have an early work in 2019 on what we called a Swiss Army Infinitesimal Jackknife, basically using this Taylor series expansion, but for approximate cross-validation and things like that. And there we were looking at theoretical and empirical behavior in that particular case. It turns out an issue with that approximation is that it breaks down in accuracy and timing in high dimensions. And so we addressed that in follow-up work. And something you may have noticed is that loss function that I showed earlier essentially assumes independence. So if I was looking at something like a negative log likelihood, it's a sum over the negative log likelihood terms. And so effectively the likelihood is factorizing. And so what if I have a time series? What if I have a spatiotemporal model? What if I want to remove points like that? Well, our paper in 2020 lends some insight to that, at least in the approximate cross-validation realm and probably in this realm as well. And all of our work in this area builds on this classical idea from statistics called the Infinitesimal Jackknife. So it's a really beautiful idea. Like so many great ideas in statistics, it really traces back to the 60s and 70s. And there, interestingly, it was sort of used as this theoretical tool for proving things like consistency and asymptotic normality. And people were like, oh man, there's no way people would write down all these derivatives. And now we have these wonderful automatic differentiation tools that are just built into our programming languages. And so we can wed their ease of use with these beautiful statistical ideas. And I'll just note some of these other pieces of literature on approximate cross-validation don't use this. They use Newton step type methods. And so it might be interesting to understand if any of that could be used in this data dropping mechanism. Okay, so let me just conclude by saying we would love you to try this out. So today I talked about this metric to check if there's a small fraction of data you can drop to change the substantive conclusions of your data analysis. We have a paper up on the archive about this that you can check out right now. And I really want to direct you to the code. So it would be lovely if you would try it out. So again, I want to emphasize my fantastic postdoc, Ryan Giordano. So that's the R. Giordano that you're seeing in this GitHub repo. ZAM influence stands for Z estimator, approximate maximum influence, because remember this works for Z estimators. It's a fun name. And it would just be fantastic if you tried this out. We would love to hear if you had problems running it. We would love to hear if you tried it on your analysis and it was robust, if you tried it on your analysis and it was not robust. We're interested to hear it all. And again, I just want to emphasize this point that, I think it was just really lovely working on this paper and being able to reproduce all of these economics analyses so exactly. I think this is something that data analysis as a whole, especially a lot of recent developments in sort of AI and machine learning, could really take a lot of lessons from. Thank you. And I'd be happy to take any additional questions.
Cool, thank you so much. So we can transition into question and discussion time if anybody has any questions.
I have a question.
Please.
That was very cool. Thanks. It's not a question, but my question is, it seems like you're almost like presenting people for their data analysis with like the best case robustness, because it seems to me like if you have observation 1 is the most influential, say, and then 2, 3, 4, say, just ordered, it almost seems like it could be that 3 and 4 together are jointly more observational than 1 and 2 because they were identified. Okay. So it almost seems like it could even be worse than what you're telling.
Yeah. And so I guess I would say that the right way to think about this in general is that we can flag non-robustness, and non-robustness is conclusive because you know that you can drop these data points and you can check that if you drop them that you get the change, but robustness is not conclusive for the reasons that you're describing, for other reasons I'm sure as well, but absolutely. So I think a really interesting point that you brought up here is that we're making this linear approximation and it's very strong. You could imagine that there are groups of data points that work together, and that's really changing. Interestingly, we have not seen that in any of the data analyses that we've done, but of course we've done a particular type of data analysis. Like all of these are in econometrics. They are particular types of data. They are particular types of analyses that people tend to use. And so I suspect, especially as we get into, people are using this in more and more diverse areas, that may come up. But I do think it's, again, worth emphasizing this point that if this flags something and you check it by rerunning your analysis, you definitely know that's not robust. And so there's always that, point that you get something from it. But yes, it could be even worse.
Thanks.
How does the influence calculation deal with data analyses done using convolutional neural net?
Okay, so there's a couple of points. So as long as everything that you're doing is differentiable, which it typically would be in a convolutional neural net, I suspect you can run this just fine. That being said, I think the reality is in a convolutional neural net that your likelihood landscape is just incredibly complex. And so I think the real issue here that I would suspect is that you are going to be getting this Taylor series expansion around one particular mode in this super complex landscape. And I don't know what the significance of that mode is. Like, it certainly isn't going to be something that's fundamentally very global, that is maybe getting at like what you would like to get at by running something like cross-validation or dropping your data. And so that would be where I would suspect an issue could arise. So that being said, I mean, you can still run it and see what happens and see if this really changes your analysis. But if this doesn't flag something, I would be especially skeptical that that means that this is robust.
Hi, Tamara, this is Yi. Yeah, very nice talk. So I really glad you have made such a great achievement doing this robustness analysis. So my question here is actually my comment is, so looks like actually normally when we do model diagnostics, we calculate the influential points. But when we do so, we just remove one point, right? We remove one point away and we refit the model, and then we calculate the so-called delta beta. Okay, so I think it's a cool idea that you introduce this W vector. So basically you generalize this influential point detection. So I think this is a very cool idea. So my first question here is, your model actually is a linear model, but it turns out that if your parameter estimate actually is smooth with respect to the sort of like a W, I think perhaps this methodology can also be generalized to some other models like the GLM, even survival models.
Oh,
right?
so just to be clear, so this technically should work for GLMs already. So let me just go back to, so it is linear in W, absolutely, but W is just sort of the data points. And so in particular, okay, so looking at this loss function here, you could just have a GLM loss function for F. And so as long as it's differentiable in theta, which I think a typical GLM would be, you're still good.
Okay, cool. Yeah. I imagine.
Survival models, I'm not as sure about though. That's an interesting question.
Yeah, but I think it's also doable. I firmly believe so.
Cool.
So my question here actually is, so here you talk about the robustness. So have you thought about actually what actually will be the metric to evaluating, how robust, the model is with respect to your data, based on your 5 function here?
Yeah. So it's pretty interesting. I mean, I feel like there's definitely a lot of things that practitioners need to think about. So what is the thing that you're reporting at the end of the day? Is it sign? Is it significance? Is it something else? And so I think that what you want to do is you want to say, does my decision change? And so if my decision is based on sign, if it's based on significance, that's the relevant phi to be looking at. And then what you really want to say is, how many data points does it take to change that decision? Or at least, as we were discussing earlier, a lower bound on the number of data points that it takes to change that decision. And so I think, it's interesting if you look at this example where we just dropped 0.05% of the data. I think it's a pretty clear-cut example where we would all be worried if dropping 0.05% of the data changed our significance. I think this is much like a p-value where as it gets larger, it becomes more of a gray area and you have to make some decisions. So it's like, is p 0.05, is everything wonderful below p 0.05 and everything horrible above it? No, of course, there's a gray area there. And I think there's a similar situation here. So in our paper, we kind of revolved around like 1% as some point that you might be worried about. But I think it ultimately depends on what you're doing, and you have to, in theory, like think a little bit about like what percentage of your data would you be worried about dropping. Of course, in theory, you should also think that about p-values and do people, I don't know, but I think if you get something that's really clear cut, like this very small percentage of the data to drop, or a very large percent, then I think it's a little more clear cut in that case. Yeah.
Thank you.
So I think there's a question in the chat, and so I'll just cover that next maybe. So thank you for the questions and this question as well. So what would you recommend in reporting scientific results to collaborators to journals in light of this robustness check tool? And is this tool extendable to inform which future data to sample and enrich in trial settings? So for number one, I hope that this is such an easy check that people can run, that if they run it, that it would be nice to report it. And I think I would also think of this as something where just because you're not robust is not damning. Just as if you have a small or a large p-value, it's not necessarily damning, that you want to report it, you want to say it, but then maybe have a little discussion about it. Like what is the meaning here? Is this bad? Is this, what does it mean that you have to drop these data points? Maybe do the analysis with the data points dropped and see what happens. But I do think it would be really cool if this were something that started getting regularly reported, again, at least in cases where it makes sense. As we were just discussing, it's not as obvious to me that you get too much out of doing this for something in a neural net architecture of any sort. But for standard analyses, I think that this could be very helpful. In terms of the second question, I think it's a really interesting idea. I guess I don't have an answer, but I think it'd be great if somebody looked into this and saw if there were settings where this could tell you about. Something we also haven't looked into is, just as for Huber robustness, there are like these robustification procedures. You could imagine that maybe there are similarly robustification procedures here. It's always a tough thing though, because isn't there that law that like, is it like Goodhart's law or something, where as soon as you make something a metric, then like it's no longer a good metric? I don't know. But I think it would still be interesting to think about these problems. So thanks for suggesting this one.
Oh, hi, Dr. Broderick. Thank you for the talk. It is very inspiring. I have a question. So my understanding of this method is that given a data, this method outputs a binary result, whether 0 if the parameter's sign cannot be changed by dropping 5% of the data, and 1 if I can drop 5% of the data to change the parameter estimate.
Let me just change that very slightly, what you're saying. So essentially, so what we output is one of these things. So one thing is we say the largest possible change by dropping some alpha percent of the data. So you could ask, like, what is the biggest change that I could get by dropping 1% of the data, for instance. And we could say, and also whenever we do that, we also tell you what data points they are. Now, what I've effectively shown in these examples is actually the last thing, the thing that's highlighted, the minimum data proportion to achieve a certain change. So let's say that I'm concerned about, the sign changing. Then I tell you what data proportion is needed for that. And so in the examples we saw, it was things like 0.05% or 0.1%. In other examples, it was things like 4 to 10%.
Okay, I see. So these three values all measure the robustness in the data. So I wonder, have you tried apply this method to this method itself? So is it possible
who watches the watchers?
So is it possible that by dropping 5% of the data can be changed from robust to non-robust or vice versa?
Right, so certainly one of those directions is true. So once we've dropped the data that causes the non-robustness, we should expect that we can't get that same level of change, at least, or we can't get any worse change because the monotonicity, like the constructed monotonicity of the influence scores, because we're removing the largest ones, and so it couldn't be worse once we've dropped those data points. I think in order to get something to be less robust, you'd have to pollute it with different data points somehow. But it might be interesting to think about what those would be.
Okay, thank you.
Cool.
Can I ask a question? So, I mean, in some sense, you're ordering the data points, right? Let's just think of a scatter plot example, right? So,
yeah.
So of course, there's one data point who's the most extreme, right? It has to be the extreme one, and there's another one which is second most extreme, another one third most extreme. So, of course, they'll change something, right? As you rank them. Is there sort of a null here? Like a specific example where you had Gaussian, you knew everything, and it was the correct model, and so in fact, I mean, there's nothing wrong with that. So you're just sort of you're labeling them as ordered in terms of their influence, but I mean that's sort of the correct model, and there's no problem. So in some sense, that's for null. So you've got something to compare with.
Well, so I would argue that it's not quite a null. So I think this is this simulated example. So this was the correct model. Everything was perfectly specified. But I don't think this is actually getting at misspecification. So there are cases here where the signal is so hidden in the noise that it's fundamentally an unstable result. So the idea here again is sort of like, if this epsilon is really dominating, like the noise is just swamping the size of the thetas and the x's, then you don't really expect the result to be stable, that you're not really able to learn the sign of theta. And I think that's intuition that I think we all have about this problem. And that's a case where we can drop some data points we find and easily change the sign.
There's no concept of a null because there is an expected, there is a most extreme and a second most extreme and a third most extreme, right?
Yes, but I'm not sure. I'm not sure if that implies. I guess I'm not sure what exactly would be a null here, but I'm not saying that there couldn't be.
Okay, it just seems like everything is correct here.
Yes, yes. So yeah, everything here is perfectly correct. There's no misspecification, and yet I guess I would still argue that there is something that we want to pick up, which is the instability, and that we could be interested in that even without misspecification being present.
So you think the conclusion you get from the whole data is not a good one here, even though it's sort of, you've simulated from an exactly known distribution, you fit the correct model, and you got.
Right, but again, remember,
you've got inference.
So it's not every time that you're fitting this model. So if I fit this model and it's the correct model and my epsilon ends are extremely tiny relative to my theta and x ends, I absolutely think that that should be stable and that this metric should return that that's fine. But if I fit this model where my theta and x ends are nearly 0 relative to my epsilon ends, my epsilon ends absolutely swamp them, then it might be that it truly takes a lot to tell me what those values are. And it might be that for a particular finite data set, that learning that theta is somewhat unstable. And that just taking away a few data points might reveal that.
So when you say changing the significance on the right, I would imagine for many of those points that are dark red, your result is non-significant most of the time because your noise is so high.
Yeah,
so when you say changing the significance, you mean passing that bound on either side. So
yeah, and actually, so something I don't have here, but if you check in the paper, is we actually have the graphs. So the graphs in the sense of what is the value that we are looking at for the significance, like the theta plus or minus, and how that changes as we drop more and more data. And so as you'd expect, it's like this kind of curve. So there's like I should draw this, but there's like this point, which is like the theta value. And then, you know, sort of like by dropping some data points, you can change the significance in like this upper direction and this lower direction. Like there's like the worst case in either direction. And at some point, one of these crosses a threshold, like a threshold of like, you know, is it now negative instead of positive or whatever. But absolutely, this means in either direction. And so like I totally agree with, I think, the implicit observation here, which is that maybe I don't care too much if I had a non-significant result to begin with, because I'm not going to be like querying it a ton. I'm just going to be like, okay, it was non-significant, whatever. But it's the significant results that change to non-significant that we probably really care about, because that's really going to change some kind of like decision-making process. And so I think this is, it's not so informative about that, but perhaps this is a bit more informative because this really was a significant result that changed to non-significant.
Right. I think I'm just, something about the intuition of those plots is I'm missing. It makes sense to me that when you have a very low signal to noise ratio, it's easy to change the sign of your estimate. That makes sense to me. I would expect that estimate to be close to 0 and easily wobble around 0. It makes less sense to me that, you know, I would also expect, if I have a very low signal to noise ratio, my estimate should be close to 0. And I think my intuition is that it would take me a lot of data to move it. I would have to take away a lot of data to move it away from 0. And I think that maybe that's, I don't know, maybe Jeremy was confused about something else.
Yeah. No, I think this is a great question. I admit that I think I am thinking of this primarily in terms of the sign, where I agree that I think my intuition accords with what we're seeing. And I think your question is absolutely making me think I need to think of a better way to convey this significance fit as well, and maybe think harder about it myself, because I don't know if I have like a super quick, like, here's the intuition in that case. But yeah, no, it's I'll definitely appreciate both of the questions.
Okay.
Maybe just a follow-up to that question. So I think the reason the significance level, so the significance result is changed, is not because the general estimate of the noise is changed, right? So you're working off the theta hat, so you're moving the point estimate around. Therefore,
yeah, so I just should be super clear, just to make sure we're all on the same page here. When we're looking at significance, the quantity of interest, the phi, is theta hat plus or minus 2 times the standard error. So the quantity of interest in the sign is just the theta hat, and in the significance, it's all of those wrapped up into one. And so we have to like think about them both simultaneously.
Yes,
absolutely.
but my point is you don't really change the sigma estimate, but you only change the theta hat. Then they give you a way to change the significance level.
Yeah, although you said, and I think this is partly what Gene was getting at, if I understand correctly, that like somehow like the idea that theta hat is also going to overcome that noise estimate is perhaps the like the sticking point. Is that?
Yeah. So I think, well, I mean, this is kind of a important work because it's identify some like the influential points in your data analysis. I'm all for that. But at the same time, I think, so to say that robustness, I think it's kind of a saying there's just a sort of an extreme situation by dropping a certain amount of the data can.
Absolutely. I can't emphasize enough that you don't necessarily have to care about this. Just like any type of sensitivity, you should ask yourself, is this a sensitivity you care about? If you think it's perfectly fine to drop a few data points and to have a different result, which I think there absolutely are analyses for which that's true, then you should not be concerned about this.
Yes, because I think the normal way to think about this, if you randomly drop 15 data points or randomly drop 0.1% of your data, does your result change?
Well, I guess I would say that's just a different way to think about it, right? Because there are some cases where you do care that there's a small part of your data that's driving a result. So again, I think microcredit's a great example. If there's one person in your town that's getting really rich off of microcredit and nobody else is, you do really care about that. You know, you really want to see that there's not like a few people that are driving the whole microcredit result, that like a lot of people are benefiting. Now, I'm not saying there aren't other ways that you could have been looking at that, but certainly like this is one thing that might flag it. So I think it just depends what you care about in your analysis for sure.
Yeah, I completely agree. This is important work, but I think people, well, I mean, some people can take it the wrong way. For example, this could help a tool for p-hiking. That's something you don't want to see people use this for.
Yeah, absolutely. There are going to be cases where this is just not a sensitivity that you care about. And I think that's just, yeah, I think in general, I mean, it's the hard part about statistics that you want to think about like what matters for the problem that you have.
Thank you very much.
Thanks.
Yeah, actually, I have a follow-up question for this exactly example. So as William mentioned that probably maybe we are not quite interested in the influential points here, but maybe we're thinking more about the parameter estimation problem or like statistical inference problem on theta. So your method, can your method give us some implication that whether the data set we have actually are able to do such an inference, right? So if you have so basically this indicates that if you have a very low signal to noise ratio, potentially your results on theta is not reproducible, basically, right?
Well, so I mean, I guess at the end of the day, so that was sort of like just trying to poke at this idea, but at the end of the day, this is really telling you, you know, exactly these quantities. So, you know, what is the largest change you can get by dropping some alpha fraction of the data? What are the changes that are achievable? And I think the interpretation of that is going to depend on the problem, whether it's something that's a worrying change in theta hat, whether it's something else. But like this is like fundamentally, you know, what it's telling you. And then everything else here is just trying to get at like, what does that mean? Right. And so I don't think of, I guess what I want to suggest is I don't think of like signal to noise as being like the fundamental thing. That's trying to get at understanding like, essentially, how is this different from other things that we already have? Because we have so many tools that are like called robustness tools, right? And so, you know, what is different between those tools and these tools? But I guess I still want to suggest that like these three things at the bottom are like the fundamental things that we're getting.
Right. So, but if the model is correct and the method sort of it's okay, and you still have this problem, then there's something like we want to change the method potentially, or improve the method, or we just feel this data set is
right. Okay. So yeah. So I think this is an interesting idea, which is like in some sense we're talking holistically about the data analysis. So like I think as statisticians we want to think about things like misspecification, like oh if I just use the right model I could fix this. And I think what's really interesting here is that we're talking about like stability instead of misspecification or modeling it. So it literally could be the data. I mean, again, let's say that I want to talk about like what is the average effect of microcredit on profits, and Bill Gates walks into town. You know, now the profits of this town are fantastically high. And the issue there, in some sense, I mean, could be seen as modeling. It could be that like we recognize that the mean wasn't really the thing that we cared about at the end of the day. We chose this parameter, but it wasn't really like the right way to express what was going on. But you could also see what's happening as a data issue, you know, that like really Bill Gates is very different from everybody else. And there are just a few data points that are driving things. What does that mean? It depends what we're trying to do. Maybe we just need to get rid of Bill Gates and look at everything else. In this particular case, it does seem like it might be a good idea to get a more direct measure of the things that we care about.
Yeah. Yeah, thanks. Yeah.
Thank you.
Any other questions? Okay, seems like people have their questions stated. Thank you so much for a really nice talk.
Yeah, thanks so much for all the questions. I mean, I think this has been a really great discussion, and thanks to everybody for showing up for the talk too.
Okay, take care, everybody.
Thank you.